Hello and welcome back to the SHA1 Performance Quest episode 2. In the past episode we have managed to write a few benchmarks and realize that our bigger brother SHA-256 is so much faster than us for some unexplainable reason. It is basically faster than us even though it shouldn't be, and it is able to process smaller chunks much faster than us. And yeah, what I'm seeing here might be helping us to fix this problem. And just to be sure we are all on the same page, let me highlight the method for you that plays a role here and why we are so much slower. So it's write. Write takes a bunch of bytes, which should actually be fed to the algorithm that does all the SHA1 magic that I have no idea of, to be honest. But as you can see, it will immediately clone its own data, clear the array or the vector that is behind that, and then it pushes all input data onto the clone, which could possibly, allocate a lot of memory. There are possibly like 2 or 3 allocations of memory happening here, which is slowing it down terribly. On the left side, you see how it's done in SHA-256. There's a fixed buffer involved that, kind of handles it. So let's have a look at whether we can have that as well. It didn't take long until the fixed buffer implementation was found in the SHA-256 sources. I actually thought it was part of the standard library initially, but I was proven wrong. However, if you look at that here, you will see that it's full of trait code, which basically implies that it was intended to be used in a very generic way. The fixed buffer that I'm building now basically throws out all the trait stuff because I'm really thinking it's my local version, as long as it is my local version. So seeing it from that perspective, I think the author of SHA-256 really had something bigger in mind, and hopefully at some point this will be part of some cryptographic library that everybody can use. And because I'm an optimist, I might have thought that putting fixed buffer from the left to the right is a simple thing, putting away some traits, exchanging some functions, and that should be it. But I have been rather wrong. It took me a while to do all the replacements. It took me a while to understand how the API of the fixed buffer actually works, because it's so much different to using a vector, which was done before. Well, it is really like 15, 20, 30 minutes until I first actually dared asking the compiler what he thinks about my work. Oh well, that wasn't as bad as expected. A few types that have to be renamed, a few functions missing. What could possibly have gone wrong here? So far, I was quite confident that this should be over in, well, probably just 5 minutes. But wait for it. Just a cutaway. Even old me must have realized by now that the basically stupid copy, paste, and fix it here, fix it there has found an end, finally. Because I realized that while watching at this output method that is supposed to produce a 20-byte SHA, by the way, that something was missing. It was a bit too short to actually produce a SHA. I was missing the SHA itself, and that was the code I just copied there out of the diff just to get it back. By the way, Sublime multi-line editing is about to happen there. How awesome is that? All the WIM people will now say, oh yeah, well, we've had that forever, and you're true, but I have never really used that, so I actually do like it since Sublime, basically. Nonetheless, it's not about Sublime, it's about Rust. I was tempted to say Ruby there, but I could hold myself back a little. Yeah, so this, what you see here, basically goes on forever, because it's the first time when I actually have to think and realize that this is trying to produce another 64-byte block. You have to imagine that the algorithm only works on 64-byte blocks, and in order to get a valid SHA, you must feed it data that is a multiple of 64. And to achieve that, they have to do a trick, I realized. They have to pad the missing bytes with zeros. And because that is happening for every input, every input will produce the same SHA if the input is correct, because the padding algorithm is always the same. So that's how that works. But I basically truncated too much there, and it takes me a while to get code back which could possibly work. At 20 times the speed, things are so much less boring, I figured. And here we are again. Some uint is deprecated, use usize. Why would that be? Well, I guess it's not quite clear how many bytes such a uint would have, especially depending on the platform or architecture that you're compiling for. So usize commonly is your supported size type. So it's 64-bit on a 64-bit platform, 32 on a 32-bit platform. So far, so good. A final rename made it, but I was wondering how I could copy that from original Rust code, right? It's from the SHA-256. And yeah, the only conclusion I can make is that even in the Rust code base, they didn't fix that, which could be fixed with the final replays apparently. So that was interesting. Set memory. This definitely was one of the tougher ones. It is a method that does not exist. For some reason it seems to work when compiling Rust C, but it doesn't work for me because it's just not there. Honestly, this was an odyssey. I tried so much. I was searching, looking, and just couldn't find an equivalent. Why would that be? Set memory is probably unsafe because it just sets memory and it doesn't use memset for that, probably calls memset in C, which is inherently unsafe, and I just don't have that piece of gorgeous, beautiful, unsafe code. Yes, so keep searching, Sebastian. Because who searches shall find. This is kind of an oddity that I found. Small cult following, totally related to Rust, and this man even puts his family pictures online, and this must be a very special site or a very, very small community if that is happening. Very, very interesting, I thought, but yeah. Still, I was looking for a set memory, and here I could probably find a lot, but not that. Yeah, the blog possibly has something for me. And one of the things that I hate about these blogs is that they don't give you any date. How old is that blog post, Is it new? 2 months ago. Oh, I've seen it there, but that was Discuss. Well, good to know. When I was recording this, I didn't realize that I was just angry and sad at the same time. And you guessed it, this goes on forever, even at 20 times the speed. I was doing a lot and trying a lot and trying to figure this one out, tried a few different modules and searched, and And I just couldn't take it anymore. I am totally ashamed of myself, but what should I say? I had to do something, and I couldn't come up with anything better than what you see here. Why try to use a method for this or a function if you can just do it yourself? I mean, come on, there must be a better way to do this, right? But well, I don't know. Fortunately, that's not a performance critical section at all, so it's alright to do it that way, yet I'm not happy about it. Moving swiftly on to clone. Clone is actually the next thing that I'm not happy about. Fortunately, I can just accelerate this, but after all, I found, or I was looking for a clone method and tried to even implement it, just to finally figure out that the reason it wanted clone and couldn't have it was me all the time. It was me who was calling the clone method on that one, even though I was having a value type. I was seeing an array and tried to call clone on array, even though arrays are just copied by value by default. So yes, I learned that the hard way. Now that the clone was over, I thought, what could happen? Well, borrow checker could happen. Closure requires unique access to self, but self buffer is already borrowed. Well, what could I do? Well, can I kind of take the buffer out of there and put it into a mutable variable and kind of trick it? No way. You cannot trick the buffer checker. This is what I learned, which is actually a good thing, that shouldn't happen. So how does SHA-256 do it? They do it like that, right? They put something into a separate variable and then this magically happens. So what if I do that as well? Clearly nothing good. The thing is that the design of SHA-256 is quite a different one because they do have a state, and the state just has the state and a process method, and we have the state as part of our SHA1 object, whereas they have the state as part of their engine. And this allows them to basically decouple the engine that later gets the process block called and pass it into the closure, which basically works apparently so. This also means that, I was quite wrong that I thought initially, wow, they have kind of over-engineered this. Look, they have an engine for this and that and kind of encapsulate this. Why would they do that? Now I know. This is why they would do that. Something that I cannot really judge is this abstraction better? Does the borrow checker in that case force you to fix your incorrect assumptions? I mean, the SHA1 that does the processing itself, is that wrong? I think it is wrong only if you have a closure here for processing. Input takes a closure and that seems to be the problem. If it wouldn't be so generic, I say, then we could probably handle that much easier. Well, probably, as I said, I can't really judge that. I just know that to fix it, I have to do it myself. So SHA1 needs to have its own SHA1 engine. But will that tiny engine suffice to defeat the diabolical borrow checker? Will he finally win the war and be able to produce gorgeous SHAs for all sorts of bystrings and inputs of this world in an unmatched speed that has never been seen before? Well, to learn that, you will have to see the next episode of the SHA1 Performance Quest. I hope you liked it, and if so, please subscribe and see you next time.